exciting series of lectures.
Thank you. Okay, so we have about 2 hours, and of course, it's a rather limited time to tell you everything about ADS-CFT correspondence, but I will try to sketch some contours of the duality and put it in the context of relativistic quantum field theories at finite temperature and density in the appropriate hydrodynamic limit, because this is what we are mostly interested in. So let me, before I remind you what we did last time, let me just comment a little bit on the list of references that you all were supposed to receive at some point, because from the questions I received yesterday and before yesterday, it's obvious that some comments are in order. So this is a list of references for the holography course, mostly the one I was given in Oxford, and of course this course is fairly long. So obviously, if you are interested in the subject seriously, you have to go to other sources to learn ADS-CFT correspondence in full glory. Now, this list starts with 7 books written on the subject in the last several years, starting from the book which was published in 2014. So it's fairly recent in the last 5 years, but nonetheless already seven monographs on ADS-CFT correspondence and its applications, in particular applications to heavy ion collisions and applications to condensed matter physics, were written by various authors. So I won't comment on them extensively, we have very short time, but if you want to learn the correspondence in detail, your best source is one of these books. So pick the favorite and learn. You don't have to. Some of them appeared before in the archive as lecture notes or some other notes, so you don't have even to buy it. You can just go to the Inspire, to the archive, and see if you like the particular text, right? And then, if you want, you can buy the book. So this is the main kind of comment that I wanted to make. Then the other publications, the other references are grouped into subjects. So we cover some of these subjects in these 4 lectures, and then it's up to you to go to particular subset of these references and learn more from the publications which are listed in the particular subsection. Okay, so this is important, and of course this implies that you have to be proactive, right? And don't wait for me to say, well, read this and this. Finally, the last comment is the following. In the very last part, in fact, on the last page of this list of references, there are some online lecture courses mentioned. They are pretty good. So these are online. So there is this interesting resource at MIT. It's free, so you can just listen lectures online and stop at any time and rewind and listen again and so on and so forth. And there are lectures on holography which appear on this resource by John McGreevy, Sean Hartnell, and Hong Liu. These are separate courses, but they are about various aspects of holography, and these are very good people, and these lectures are highly recommended. So you can use this resource very extensively. Okay, so this is all I wanted to say about references. If there are other questions about this list, please ask me while I'm still here. So let me remind you very briefly what we were discussing last time. So we had this expectation value of the energy momentum tensor operator, which we denoted by T mu nu, and we considered this hydrodynamic approximation to a microscopic theory, which was written in the form of a derivative expansion. So it started with T mu nu node, and then T mu nu 1, and this node 1 and 2 and so on indicated the number of derivatives involved in the particular term. So there are no derivatives here. There is one derivative, so this involves du, and these terms involve second derivative of u with respect to x and t, and so on. And then you can combine this derivative expansion with, so if you combine this with conservation law, And again, so I mentioned last time, so everything can be done in curved space-time if you like. So you can replace this derivative, always replace the derivative of covariant derivative in your favorite curved space-time, and you will get equations of hydrodynamics in curved space-time. All right. So if you combine this expansion with a conservation law, you'll get equations of motion. So equations of motion, if you have only 0th order, this will give you Euler equation. Euler equation. If you have 0 plus 1, then it will be Navier-Stokes. If you have 0 plus 1 plus 2, this will be Barnett, and so on. And in fact, so 0 plus 1 plus 2 plus 3, nobody bothered to write down. So if you want your name attached to some set of equations, then you can, yeah, you can do it. In fact, so for each entry here, we have an explicit expression for the expectation value of T mu. So T mu naught, remind you, was epsilon u nu plus pressure times delta mu nu, where delta mu nu was this operator, this projector, which I can write in curved space-time. So it's G mu nu, but it would be Minkowski if we use flat space-time. And I remind you that our signature is minus plus plus plus, unlike in particles physics, because we are using string theory and gravity. All right, so this is T naught, and then we had expression 41. And expression 41 contained dissipative terms. And so let me just write it down, because we will need it shortly. Just remind you this. So d alpha u beta plus d beta u alpha minus 2 over d in d space-time dimensions, g alpha beta d lambda u lambda, and then a second term which is a trace of this whole thing, and the trace of the whole thing is proportional to bulk viscosity zeta. So there are two transport coefficients, shear viscosity and bulk viscosity, that enter at order 1. And you can continue this, and you can construct this. This is called the first order hydro, first order hydrodynamics, and you can construct second order hydrodynamics by analyzing tensor structures in T2 and so on. So at the moment, what is known, the second order hydro was constructed not so long ago, about 10 or 15 years ago. And, but it's known, so the transport coefficients were classified. Partially, it's also known to third order. So third order hydro is only partially known. There is no entropy current analysis which has been done. So this is some open problem if you want to look at these issues. This is something that a dedicated graduate student or a postdoc can actually do. And then beyond this, nothing is known. In particular, there is this question of how many transport coefficients do you have at each order n, right? So given an order n, how many transport coefficients do you have? How they grow with n? Is it exponential growth? Is it some polynomial growth or so on? So this is unknown, and in fact, it can be analyzed in particular with the help of computer algebra. So at some point in the past, my former graduate students in Oxford wrote this code, but they haven't finished this sort of the full program. So this is an open question. Fine. So we have this relativistic hydro. Sorry. Let me here use a covariant derivative just to be consistent. I started writing everything in curved space-time, so just replace this covariant derivative. Fine. And we also had another discussion. So this was just a hydro discussion, a relativistic hydro discussion. And we had another discussion which was more general. This was a discussion of a linear response. And you have a system which is sitting in equilibrium, and then you perturb it with some operator O, and then the system goes back to equilibrium, and this gives you a general formula which allows you to compute various transport coefficients and anything else that it matters. So we had this, I think we had this form. So we had a generic formula, but we also had the linear response formula for the operator O, which was a set of particular components of energy momentum tensor Txy. So I choose xy because I want So my system is homogeneous and isotropic. This is for simplicity. And then I can choose z coordinate along momentum q, right? So this is my choice. And this means that in Fourier space, I have everything proportional to e to the minus I omega t plus I q z, where q is the third component of my q. So it will be 0, 0, q, like this. So these are notations which I'm going to use in the rest of this lecture. All right. Any questions about what we are doing? Right. So what I'm about to write down is the expression for the change in the value of the expectation value of the operator O under the perturbation all right. So this formula appeared, or its analog appeared in the previous set of lectures, and therefore I won't repeat it here. But this is a generic linear response. So you have a Hamiltonian, and then you perturb the system with some external influence, and this external influence could be, for example, external gravitational wave. All right, so remember, we had this formula where the role of H was played by the symbol lambda, right? So lambda A, whatever it was. So I send external gravitational wave to my system. The gravitational wave does something to your system. It squeezes it, it creates shear, it does something depending on what kind of polarization I want to choose. And here I want to choose a polarization HXY. So my metric G mu nu is Minkowski, and then I have little h mu nu, and in this little h mu nu, I'm interested only in polarization HXY of diagonal terms. Okay. So the response of the expectation value of the energy momentum tensor to this gravitational wave, to first order, we assume that this gravitational wave, this perturbation is small. So you can put epsilon if you want, right? So this is to linear order in epsilon. Of course, there are corrections to this, but to linear order in epsilon, we have this relationship between the change in the expectation value of T mu nu and the external amplitude of the gravitational wave. Where G retarded is the retarded correlation, two-point correlation function of the commutator of the components of the stress energy tensor, as we wrote down last time. Okay? So the moral of the story is that if I know the correlation function of the stress energy tensor in equilibrium for my system of interest, for example, for water, then I can compute how the expectation value of Txy changes if I send gravitational wave to my system. Okay, so you may say, well, so what? You have this formula, and is it useful in any sense? And it is really useful because we have also independent of this, so this is generic. Now, this is true in the hydrodynamic approximation where frequencies and momenta are very, very small. Okay, so this is generic, and this is the expansion of T mu nu for small omega and small q. And this expansion involves, if I ignore all the tail from T2 and later on, it involves, for example, a term which contains shear viscosity. So I can do a calculation by saying that my metric G mu nu here is exactly of this form. So it's Minkowski plus a small perturbation h mu nu, which depends on t and z, right, in this homogeneous environment. And just do the calculation, just plug into this crocodile here in the formula, and can compute what hydrodynamics tells us generically about the perturbation of the stress energy tensor from equilibrium. So do this. This is an exercise. I'm not going to do it on a board, but please, if you're interested in the subject, please do it yourself. And you will discover a curious relationship for delta Txy. So it will have the following form: minus pressure times hxy minus shear viscosity, the derivative of hxy with respect to time, and then there will be other coefficients. I will write two of them, although we won't really need them, but just to illustrate that this is an infinite series, and you can continue this. Right, so this term comes from T2, okay? And this guy comes from T1, okay? And then you can continue this indefinitely, right? So this formula follows from here. You are responsible for derivation of this formula. Takes some time, but it's relatively straightforward. And now you can do the following. So let's just compare, right? So we have a left-hand side. So this goes into the left-hand side. And you use Fourier. So your hxy will be proportional to some signal, and then there will be a Fourier component, which depends on t and q like this. So this means that in this, so you have to substitute this into this formula, take a derivative, and take a derivative, omega jumps downstairs, and 2 omegas jump downstairs in this term, and you will write down this expression in a Fourier space. And then you have the following relationship. So also put q for simplicity. Let's just put q to 0 for a moment. And you will discover the following, that the left-hand side will contain the following expression. So it will be I omega eta h xy plus corrections. And here you have minus g retarded of particular components of t mu computed at 0 momentum. We put momentum to spatial momentum to 0 times hxy. And therefore, you can cancel hxy on both sides and say that, well, you just have the formula for g retarded, xy comma xy of omega 0 equal to minus I omega eta plus various other terms, which will depend on higher powers of omega, and also q, but q, we put q to 0. So this means that if you are interested in shear viscosity, you can write down the formula that viscosity is, with a minus sign, the limit of omega going to 0, then you have to divide by omega, and you take the imaginary part of your retarded Green's function of particular components of the energy momentum tensor of omega and 0. Okay? So this is an example. This is an example of the so-called Green-Kubo formula, so sometimes just called Kubo formulas, which tells you something rather interesting. So in order to, so suppose you have a system, it could be complicated microscopic system, and you are interested in, for example, shear viscosity, how to compute shear viscosity in the system. So this formula tells you that shear viscosity will be proportional to the limit, to the 0 frequency limit of a particular correlation function, equilibrium correlation function, this is important, of a particular operator, which happens to be an operator of particular components of energy momentum tensor. So if you have some means in your theory, in microscopic theory, to calculate correlation functions of this type, then you can do this limit and you can recover shear viscosity. Okay? So this is just a first example, a very simple example of a general formalism which was developed around 1950s by various smart people. And let me just give you a reference here, because we don't have time to develop this any further. But see, for example, in the archive there is this paper 1610 01 081 and references therein. Right, so this is important, right? So the paper itself is important, but the references are equally important, or the history, because at the moment, what happens, so people in the 1950s, they wrote down these formulas for the transport coefficients of the first order hydrodynamics, because second order hydrodynamics, nobody was interested at the time, it wasn't developed. And there is a set of these formulas by Green, Kuba, and Lüttinger. So in particular, there is this nice paper of Lüttinger or Lüttinger in, I think, 1963, where he derives basically this formula for shear viscosity using precisely this gravitational wave as an external source. And then he has a very modest footnote in his paper saying that if gravity didn't exist, it should have been invented for the purposes of this paper, right? So that's yeah, very modest guy. Anyway, so so the moral of the story is that there is a set of Kuba formula, rather recently, I think around 2011 or so, this was generalized to transport coefficients beyond first order hydrodynamics. Because in second order, you have, as I said, you have additional coefficients, right? So you have, so you have eta, you have zeta, and then you have these coefficients which are known as tau pi, and then there is lambda 1, lambda 2, lambda 3, kappa, and so on. And then there is so this is first order, this is second order, and then there is a third order, and you have this theta 1, theta 2, some transport coefficients. And for all of them, okay, at least for these and these and these, there is a set of Kuba formulas. If you are interested in second order hydro, then the Kuba formulas will involve third order correlators. So it will be, this is a 2-point function. And if you're interested in these coefficients, then you should write down a set of Kuba formulas for which involve 3-point functions of energy momentum tensor. And presumably this goes on. So another open question, well, perhaps not terribly exciting, but nobody bothered to write down the complete system, right? So it's obvious that there should be like a Bogoliubov type of Bogoliubov chain type equation, which expresses generically transport coefficients of order n through the correlation function of various operators of conserved charges of order n minus 1, right here, right? So that's a, but nobody has written this this set of equations, so perhaps you would be interested in doing precisely that. Okay, any questions? Yes, please.
Is that because people are procrastinating, or is there mathematical difficulty?
Sorry, could you repeat? Is it
because people are procrastinating to write it down?
Yes, yes.
There's no mathematical difficulty?
There is no, well, of course, it's not entirely trivial, right? So just look at this paper and see, just to derive the appropriate formulas for the second order coefficients already requires a little bit of calculation. Yeah, shall we say, okay? So whether the generic case is straightforward or not, I simply don't know. Given especially the fact that generically we don't even know the explicit structure of this term beyond the third order hydro, right? And maybe it's not even necessary, I don't know, right? So maybe it's impossible to do, that's also it's a possibility. Maybe it's not necessary, right? In the sense that you would never, so your computer can generate these terms, for example, right? And then you have to do the entropy analysis and kind of, maybe the pattern is such that it's impossible for order n to write down explicitly the expression which tells you that I take n-1 order correlator of appropriate components of T mu, take the appropriate limits, and I get precisely this coefficient, right? So I don't know. So this is an open question, right? So it's quite possible that this whole enterprise is doomed to failure. So that's right. But I'm just saying that these are things which nobody did before, and maybe it's interesting to look into them. Okay. Other questions? All right. Okay, very good. So now let me come to the question of duality finally. Yeah, so you again, so just to finish maybe hydro discussion, I hope you did the exercise. So we worked with a conserved quantity, which was T mu, right? But I ask you to do the exercise taking a simpler case when you have a conserved current, G mu, equal to 0, right? So in this case, the appropriate expansion, the hydro derivative expansion, can also be written in a similar spirit, right? So you have these infinite number of terms, and they are written in the following way. So there is a 0th order term which involves velocity. So I would like to emphasize that what you're doing here when you write down these expressions, you're doing precisely what one is doing in effective theory, right? So you write down all operators, all expressions which are compatible with the symmetries of the problem, right? So if you have a tensor T mu, right, it's symmetric, right? So you write down all tensor structures which involve mu and nu as free indices, and they better be symmetric. So here you have one index. So you construct out of ingredients that you have, and your ingredients involve symmetric, if it is a curved spacetime, even is flat, it will be Minkowski, and for velocity u mu, right? You don't have anything else. So you combine them in a way that that contains a number of derivatives, 0 number of derivatives, 1 derivative, or 2 derivatives, and so on, and compatible with all the symmetries of the problem. So so here you have the following structure. So again, this delta and nu rho, and then so this is first order hydro, and then the second order hydro will involve more terms like this, and you can so this is a covariant. So this is known as constitutive relation. And it's written in covariant form, right? So this is a covariant expression. But if you want to appreciate the physical meaning of the constitutive relation here, or for example for T mu, it's better to write it in the rest frame of a fluid, right? Because this is written generically for a fluid which is moving with 4 velocity u mu. But if you want to go to the rest frame of a fluid, then you discover that this constitutive relation in the rest frame, so in rest frame of fluid, so this covariant relation happily tells you that there are components jk, so k equal to x, y, z, and these components are proportional with minus d to the gradient of the charge plus corrections. And this is known of course as the so-called fixed law of diffusion, right? It just tells you that if you have inhomogeneous distribution of charge in space, then there will be a current, and the current will be proportional to the gradient of the charge. It's nothing really very fancy here, right? So this is a physical interpretation of what you have, and you combine this with conservation law, right? You combine this equation with the conservation law, and you get nothing but a diffusion equation for rho. Right, so you have this equation with d, right, plus d, and then Laplacian acting on rho equal to 0. Okay, so I would like to, so before going to duality, I just want you to appreciate the concept of hydrodynamic approximation to any system, right, to any theory, quantum field theory or classical, doesn't matter, how it works, right? So it's built thinking of conserved densities of conserved charges in the system, right? So your basic variables, out of Avogadro number of variables, right? If you're close to equilibrium, so in equilibrium, in full equilibrium, all you have, your whole system is characterized by collection of conserved charges, total energy, total angular momentum, total electric charge, and so on. This is equilibrium. There are no fluxes. Everything is dead. Everything has been cooked already, right? So it's completed. So then you go slightly out of equilibrium, And you still don't need this Avogadro number of variables of individual molecules. But how do you describe what are the basic degrees of freedom in your system when you go slightly out of equilibrium? Well, in equilibrium, these are constant densities of charges, such as rho, right? Rho equilibrium equal to constant. And then you go out of equilibrium, so natural guess, it's a guess. A natural guess would be to say, well, fine, I still have my variable rho, but now I allow this variable to depend on time and space. Not very sharply, not on a microscopic scale, but on some scale which is much larger than, for example, mean free path or some other macroscopic scale. All right? So the moral of the story, when you say the word hydrodynamics, fluid dynamics, your basic degrees of freedom in fluid dynamics are densities of conserved charges. So you have microscopically, you have this, J mu. So J mu has 4 components. J naught, which is rho, right? And then Ji, the current components. So in hydro approximation, your main component is, not main, but the only degrees of freedom of significance is rho. And then you have 3 extra pieces in this expression, in this operator, which you have to express somehow through rho and derivatives of rho. Because this is your degree of freedom, rho. There is nothing else. So in order to do this, you write down constitutive relations by hand as an effective theory. Like, it must be compatible with all the symmetries that you have, but this is, if you want, this is a guess, right? It doesn't follow. It would be fantastic that if this follows from, for example, Hamiltonian of your microscopic system. And in kinetic theory, it does. In kinetic theory, you can do it. But generically, you cannot. It's just, you're just making a guess. So then, fine. Then you have only one degree of freedom, like the one which describes hydrodynamic degrees of freedom, which is rho in this case. And then other components of the current are expressed through rho and derivatives of rho. And the same story here. So here you have T mu. In equilibrium, the only components of T mu that matter are T naught, right? So this is energy density in equilibrium, and momentum, which is T naught I, and it's the same as U naught UI, right, or PI. So these are momenta or velocities, doesn't matter, right? So altogether there are 4, right? 3 momenta, spatial momenta, and 1 energy density. So these are hydrodynamic degrees of freedom. Equations of motion, Navier-Stokes equations and so on, will be equations for these 4 components. All other components, you have many more, right? In T mu, you have many more. So these other components must be expressed via constitutive relations through basic variables epsilon and pi or ui and derivatives thereof. And this is exactly what constitutive relation is doing for you. All right? So this is the meaning of hydro as a conceptual approach. This is effective field theory approach to hydrodynamics, relativistic or not. Okay? Any questions about this? Because we're, yeah, please. Safe in what sense?
In what sense? You know, it's that Taylor expansion, or you don't have a small parameter.
It's basically, I mean, if you go to rest frame of a fluid, it becomes, the physical meaning of this equation becomes transparent. In terms of how safe is or not safe, this is a separate question. So one thing which we haven't discussed is I'm writing down expansions all the time, right? I didn't say anything about the convergence of the expansion, right? I didn't even discuss it. So these are formal series. And the question of, for example, is it asymptotic series? Is it convergent series? That is a separate question, right? So we are writing formal series. So in terms of safety, it's a delicate matter. It's a delicate matter. Other questions? All right. If there are no other questions, then let's see. Let's just go to duality. So for some reason, just 1 second. There is another reference here. I actually don't remember what, but I wrote it here, so it must be important. I think it's our review with Demson, where all this machinery is equipped with words. It's also in the reference list, but it's an old review, but useful because if you want to study it kind of line by line, you need some words in between, right? And then, yeah, so, okay. Fine. Okay, so duality. So why, let me remind you the goal, right? Why the whole discussion is rotating around this hydro and these Kubo formulas and so on and so forth. I remind you that in order to understand the behavior of strongly interacting systems, for example, strongly interacting fluids such as quark gluon plasma, one example, we need thermodynamics of that system, right? So equation of state, speed of sound, entropy, pressure, and so on, which we in principle can get from the lattice calculations. In principle, it's not easy, but it's possible. But we also need transport properties, because this plasma ball is expanding, we need to solve Navier-Stokes equations. Navier-Stokes equations do contain these coefficients. And these coefficients, remember what kind of microscopic theory is there. So these are coefficients of QCD. So we need to compute transport coefficients somehow from first principles, from Lagrangian of QCD, ideally. And we need some tools of how to do it, right? And the standard tool, which I described last time and today, is via Kubo formulae. And Kubo formulas will require the knowledge of the correlation function of specific operators, in this case, the correlation function of T mu nu, right, T rho sigma, in equilibrium at finite temperature. And if you have some conserved currents, so you need some correlation function of currents. Okay? So if you know these guys, you know transport. Okay? So the question is there some tool that allows you to compute these correlation functions in real time? And that's important to stress, that all this business with transport coefficients must involve real-time correlators. You cannot do Euclidean. You cannot extract it from Euclidean correlator. Unless you know Euclidean correlator absolutely precisely. Then you say, I do analytic continuation and everything is fine. But on a lattice, of course, you never compute anything precisely, right? There's error bars, and then you compute only in a small region of the momentum space, right? So there is no way you can analytically continue whatever you get from a lattice to get something sensible. Okay? So we need some tool that would tell us how to compute these correlation functions of QCD, or at least some theory, right? So let's not be too ambitious. Any theory to begin with, right? Because nothing was known up to the year 2002. Fine. So here duality may help. And let me proceed now with the duality part, and then we'll have a break, and then we'll continue to that. Any questions about the motivation and right? So it's important to keep the line sort of in your mind why we are doing what we are doing, right? Not to drown in these formulas and so on, right? So that should be clear. If it's not clear, ask me. That's important. All right. So duality. I hope most of you, well, you were at my public talk, right? So I gave various examples. Some of them are sort of primitive, right, of what duality is. A duality can be understood as a change of variables. So we are looking for correlation function of these guys, for example, right? And in quantum field theory, yeah, so let me see. So this is duality. So in quantum field theory, we know how to compute correlation functions of operator O. Right, so let me write this rather generic expression schematically. So we know that if we have a functional integral over some fields, it could be QCD fields, of the action, I will write it in Euclidean, but it doesn't really matter that much. And then there is a term which involves this O of interest. Then we can get the correlator, so from generating, so this is known as generating functional of Green's functions, right, of G. And I won't say anything about this, but again, this is a hyperlink for people who don't remember this very well. I remind you that in Euclidean spacetime, when you're dealing with Euclidean spacetime, there is only one two-point function, right? There's only one correlator. If you go to Minkowski spacetime, you encounter a multitude of these correlators, right? There are retarded, advanced, Feynman, Weidmann, and God knows what, right? So all depending on what kind of boundary conditions in your field, right? So when I say generating functional of G, I mean here the sort of a set of these G's if we are talking about Minkowski, and one G, Euclidean G, if we are talking about Euclidean spacetime. But this duality holography would allow you to compute any of them, so that is good. Fine. So duality, so I like to think about duality as of change of variables in functional integral, because indeed you are integrating over d phi, and therefore phi is a dummy variable. I can choose a better variable to take my integral if I know a clever change of variables. All right, so I gave you in my talk, I gave you this primitive example. Well, okay, if you think they're too primitive, I will give you another one. So, of dx and then 1 minus alpha squared x squared, right? And this thing, by change of variable, is easily calculated, right? But you have to change the variables from x to y in the following way. So your alpha x is equal to sine y, and this is because you know trigonometry, and you know that sine squared plus cosine squared is equal to 1. So this thing in the denominator looks suspiciously like 1 minus cosine squared, and so this allows you to compute this integral immediately. Let me give you an exercise just for people who are, well, for the break. Let's see, it's approaching fast. I must say, so I spent the last 3 months in Moscow University, and one of the interesting things which I encountered there, which wasn't around when I was a student, was the following. So now students of the last years, they have something which is called the Integration Championship. So there is a Moscow Integration Championship. And well, people take integral with time, like it's a competition and so on, and there are prizes, and yeah, so it's kind of cute. Yeah, so exercise. So here is the integral from minus infinity to infinity, e to the minus x plus alpha over x squared dx. All right. Let's put alpha greater than 0, although this is not very important. Show that this is equal to square root of pi e to the minus 4 alpha using change of variables. 2 changes variables. All right. So so this is just an example of how useful change in variables can be for ordinary integrals. But there could be more serious things. One of them is related to the so-called Poisson summation formula, which you might know from mathematical physics courses. And it involves Fourier transform. It's a beautiful, I mean, the whole thing of duality, of course, is a mathematical discipline, so it goes, there is a Pontryagin duality, and then there is harmonic analysis. So this is a rather extended subject. Unfortunately, it doesn't help. This mathematics doesn't help with ADS CFT, but nonetheless. So okay, the last thing before the break. Let me see. So Poisson summation formula. And Poisson summation formula tells you the following. So suppose you have a function f, let's say f of x, right, which is smooth. Yeah, on a line, right? Then there is this wonderful formula which tells you that if I take the values of this function at integer values of x, so n belongs to z, then it is exactly the same as the sum over k, which also belongs to z, of f hat of k, where f hat is the Fourier image. So f hat is Fourier transform of f. All right. So more specifically, so you have f hat of b equal to integral from minus infinity to infinity f of a e to the 2 pi I b a dA. Okay. Now, just to give you another example of this application of this transformation, and then we discuss it. Suppose that f of a, so e.g. f of a is equal to e to the minus beta pi a squared. Then you can easily calculate Fourier transform, and Fourier transform is beta to minus 1/2 e to the minus pi b squared divided by beta. And therefore, so this means that the sum over n, which belongs to z, of e to the minus pi n squared beta can be written as 1 over square root of beta sum over k, which belongs to z, of e to the minus pi k squared divided by beta. All right, this is known as Jacobi formula. And by the way, so it's an exercise to prove, right, for you, exercise for you, to prove Poisson summation formula. You can look up, I mean, the proof is in any book on functional analysis, but you can look at Courant and Hilbert. Volume 1 of Methods of Mathematical Physics, which is an extremely useful book regardless of Poisson summation formula. But look what happens, right? So it's a change of variables of sorts, right? So now we change variables in this rather non-linear way. So here it was straightforward, right? I mean, this is really, here it's slightly more involved, right? So we go from x or from n to k. And the transition from n to k involves integral transform, meaning Fourier transform in this case. Right? So you do a Fourier transform, but nonetheless your partition function, let's call it z, remains the same. So you just change the dummy index k, right? And the function remains the same. So whether this is useful, you can judge yourself. So here is the application of this Poisson summation formula for this particular exponent. But you may recognize this from quantum mechanics. So this is nothing but the partition function of the two-dimensional rotator, right? So this is z of two-dimensional rotator, which is a two-dimensional model of a molecule, right, in 2 dimensions, which is rotating like this, and then in spatial dimension 2, right? So you can write down the Schrödinger equation for this, minus h squared, h bar squared, over 2i, where I is a moment of inertia, d2 d phi squared, right, on psi equal to e psi, and you find the energy levels, EL, which are h bar squared divided by 2i times L squared, where L is an integer, right? And then you take a trace e to the minus beta h over all eigenstates, and you arrive at this expression. So this is your z for the two-dimensional rotator. Now, you can say, so this is z at beta, where beta is inverse temperature, right? So I always use beta is 1 over t. So this is your partition function. And Poisson summation formula allows you to rewrite this partition function in such a way that in the exponent you have 1 over beta, not beta. So this means that there is a relationship for the partition function of the rotator. So z of beta can be rewritten as square root of beta, z, the same type of partition function, but now of 1 over beta. And this is an example, maybe the simplest example, quantum mechanical example of a duality transformation, right? You take, this is a parameter, right? So you want to compute z at value of parameter, whatever it is, and you can do it by using this formula. And if your parameter is large, for example, right, then this transformation maps z into the same z, but now the parameter here will be small. So if z is beta is equal to 100, so this is 10 to minus 2. So this is useful because, for example, here, well, it's the opposite actually, right? So here you know very well that if beta is very large, the temperature is small, beta is very large, you can neglect the whole tail in this expansion, take only the first term. But suppose the beta is small. If beta is small, then you have to sum this function. It's n squared, mind you, right? So it's not n. It's not a geometric progression. So this is, you don't know how to do it, but this formula tells you that the asymptotic value for small beta is just given by the first term in this equivalent expression, right, which is given by the duality transform. So this is an example of a strong weak duality. Suppose you want to calculate this at strong coupling beta, right? You don't know how, but duality tells you, actually this is equal to that, so your strong coupling here is inverted to something weak, and here you immediately write down the answer. Okay? So this is the simplest example of duality, and after the break, we will write down a similar formula for gauge theory, and this allows us to compute, for example, transport coefficients such as viscosity. Okay, let's have a break for 10 minutes.